Hello everyone. The title of this research paper is Exploring Generative Classifier for Adversarial Robustness. My team is from the National University of Singapore. This presentation will talk about the motivation, the models, the attacks used, followed by the result and the conclusion. Research has shown that deep neural networks can be extremely vulnerable to adversarial attacks. Even very small perturbations on input pixel may result in drastic decrease in prediction accuracy. Most deep learning models are discriminative and approximate the conditional probability P of y given x, where x is sample data. On the other hand, generative classifiers model the joint distribution P of x and y and predict according to base rules. For discriminative models, it is very common to perform various adversarial training techniques like data augmentation during training stage in order to improve the robustness. The robustness of generative models is reflected from the choice and parameters of the likelihood. The better the parameters, the better the joint probability prediction. In this project, we will compare the robustness of various discriminative and generative models against black box and white box attacks. We will compare 12 models against 5 gradient-based and 5 decision-based attacks, each with 5 different epsilon values. MNIST dataset with 1,000 data points for each epsilon value. Accuracy of results are captured for comparison. Here is the list of the classifier models that will be used in this paper. There will be 5 discriminative models and 7 generative models. Here is the list of the attack models. Gradient-based attack require explicit access to the gradient of the specific model's loss functions. Decision-based attacks only require the prediction of the models. These are some example images from our gradient-based attack. Besides these 4, we have also tested some of our models using the Kalini and Werner attack, but unfortunately it is too slow on other models, so we do not have an image example here. These are some example images from our decision-based attack.
So here are the results of our experiment. For gradient-based attacks, we can see a clear trend that generative models outperform their discriminative counterparts across the spectrum of different attacks in this category. This validates our proposition that generative models are more robust against adversarial attacks in general. With explicit access to the gradients of the model's loss function, the various attacks are able to exploit the discriminative models more by optimizing the amount of perturbation needed to launch a successful attack. For decision-based attacks, the difference in performance of the generative models and their discriminative counterparts tend to fluctuate and becomes less of a clear cut. For image, noise-based, and blur-based attacks, perhaps because of the simplicity of the inherent randomness associated with the attacks, both generative and discriminative models perform similarly. However, for more advanced contrast reduction attacks, the general trend is that generative models tend to outperform their discriminative counterparts. Upon taking a closer look on linear search and binary search contrast reduction attack, we can see that CNN variational autoencoder and fully connected control variational autoencoder perform better under these attacks compared to their discriminative counterpart. However, logistic regression and Gaussian matrix model performance are relatively similar. We suspect that this is due to Gaussian matrix models distribution modeling overfits training data. As you can see on the left, for the following 3 attacks, we observe that the performances are quite similar across all classifier models. On the right-hand side, we have included the accuracy result of fully connected control variational autoencoder on the 3 attacks up to perturbation level epsilon equals to 1. Control variational autoencoder accuracy only starts to decline faster from epsilon equal to 0.4 onwards, which is not fully captured in our experimentation with standard L2. This is due to the fact that beyond 0.5, the perturbation will be visible to naked eye and the attack defeats its purpose of fooling humans. In a nutshell, we have successfully demonstrated that generative classifiers are indeed more robust against various adversarial attacks by modeling the joint distribution of samples and labels. However, generative models suffer from longer test time due to inference. Since test time is a deciding factor when deploying machine learning models to use cases such as autonomous vehicle and robotics, there are still issues need to be addressed before generative classifiers can make a significant impact to real-life application. That's all for our presentation. Thank you for your attention.